Now we can define the governing equations and add the boundary conditions. Start by double-clicking Setup in the Workbench window. When the Fluent launcher opens, as before, ensure double precision is checked, and that solver processes is set to the number of CPU cores on your computer. Once this is set up, click Start to start Fluent. Once Fluent is open, we should see our geometry in the view. To begin refining the governing equations, ensure that Steady is selected. We can further alter the governing equations of our mathematical model under the Models option in the tree. Expanding it and double-clicking on Viscous, we can change the model to laminar and click OK. This tells the Fluent solver that these are the governing equations we want to solve. We enforce the steady and laminar assumptions. The Newtonian and incompressible assumptions are included by default, and we will work to better define them next. Back in Fluent, to further define the governing equations, we need to specify material properties and boundary conditions. Under Materials in the tree, expand it, expand Fluid, and double-click on Air. Here we can specify the properties of the flow fluid. We can enter a density of 997 kilograms per meter cubed to match the value given in the problem statement. Similarly, we can enter 8.55 times 10 to the negative 4 to give the desired viscosity value. Finally, click Change/Create, and we can close this window. Next, to define the boundary conditions, we can double-click it in the tree. Here, we can see a list of all of our boundaries. Start by selecting Inlet in the list, and at the bottom, ensure it is set to Velocity Inlet, and click Edit. In the new window, we can enter the inlet velocity of 5 micrometers per second. Since we can see the desired units are meters per second, we can enter 5e-6 to get the appropriate velocity. From the listed velocity specification method, the solver is setting the velocity normal to the boundary to the prescribed value, which is what we want. So we can click Apply and close this window. Next, select Outlet in the list. Ensure it is set to Pressure Outlet and click Edit. In the new window, ensure the gauge pressure is 0 pascals and click Apply and close the window. Next, at the bottom, Click Operating Conditions. The pressure condition at the outlet was set as a gauge pressure, meaning it is relative to a given reference value. Using gauge pressures is useful to avoid errors caused by small differences of large numbers being saved to memory. To reduce this, we can change the operating pressure to the true absolute pressure at the outlet of 300 pascals. Since we expect the magnitude of the pressure variation in the flow to be small, this will help to reduce the round-off errors. Click OK to save this information. Lastly, click the wall inner, wall outer, and wall pillar boundaries and ensure they are all set to wall. This automatically applies the no slip and no penetration boundary conditions, so we do not need to make any changes. Doing this fully defines our mathematical model that we can now begin to solve. Make sure to save your project.